Hello, and welcome to the next section of our tutorial series, where we will show you how to quality filter and trim our FASTQ files to generate FASTA files. Remember that FASTQ files contain both sequences and quality score information, which we will utilize in this tutorial to clean our data. Data cleaning is absolutely critical so that you can trust your results at the end of your analysis. Amplicon sequencing involves the use of degenerate primers. Degenerate primers contain a mix of nucleotide bases at one or more sites on your genetic sequence of interest, in this case, the V4 region of the 16S rRNA. They are useful when you want to isolate similar genetic sequences from a variety of species where primer binding sites may not be identical. For more information, please click the link below. So due to the degeneracy of the primers, they tend to introduce non-biological variation. As such, it is important to cut them off, particularly if you're going to perform any sort of single nucleotide resolution clustering. So here we have our primers in a FASTA file provided by the sequencing center named primers.fa. So let's take a look at what this looks like. So there's the primers in a FASTA file that they use to amplify the DNA. So the first thing we want to do is make sure the primers are where they're supposed to be, that is, at the front and end of our sequences in the FASTQ files. This is another instance where the functionality of commands in usearch make this rather easy to check. So we're going to take advantage of that. And this will be done with the command search_oligodb. However, it is rather time-consuming to run that command on all of our sequences. So as long as our samples were all from the same sequencing run, we can randomly subset a smaller portion of them to check if the primers are indeed at the front and end of our sequences. So first we'll run a command called _subsample. So let me type this out first, and then I will go through the command to explain it. So there's our fasttext subsample, and remember we generated all samples merge.fq in the previous step. And let's denote our sample size, and let's make our output file, and let's call it all sub for primer check.fq. Okay, so here in this command, we are randomly subsampling 5,000 sequence from the total and creating a file we name all sub for primer check.fq. So let's run that. And here we get some output, and now it's done. So after running a command like this, I'd just like to do a quick check of what we just created. And we can see that we have sequences and quality score information in there. So now that we have subsampled 5,000 sequences, let's run the search oligodb command in order to check where our primers are landing in these sequences. Here we go. You search _oligodb, and then the file we just created. And db is our database, or the primers to check against, and that's our primers.fa. And we then specified that we wanted to check both strands, so both directions. And we specify user out, primer hits, .txt, and then one more argument, which is user fields. And we specify the query, q low, q high, plus q, and strand. So what does this command mean? So this command is searching for the primers in that subset of sequences and generating an output file called primer_hits.txt, which will contain the results. We denoted in the last argument that the file will have 4 columns per line: the sequence ID, which is the query, the start position of where a primer aligned, which we denote as Q low, the final position of where primer hits, Q high, and then if it's on the plus or minus strand for whether the primer was in the same orientation or if it's the reverse complement that was matched. So let's run that. All good. So let's take a quick look at our output file. Great. So looking through the file, we consistently see that there is a hit to the first 19 base pairs of a sequence and the last 20. So here's the beginning of the file, which is head. We do head primer hits.txt. And just to make sure that that is consistent with the end of the file, we'll use tail. And indeed, it's the same all the way down. So this tells us things are as we expect them to be, and we could proceed to trim off the first 19 and the last 20 base pairs of each sequence to remove our primers, as we will not be using them here on out. So to do this, we'll use a command from vsearch called fastqfilter. And this will filter based on maximum expected error. And you can click the link below to read more about what that is. But for a little explanation, so quality filtering, again, is critical in reducing the abundance and impact of spurious sequences. There's an intrinsic error rate to all sequencing technologies and DNA polymerases that will consistently be generating some portion of sequences that vary from their true biological origin. And this can substantially inflate metrics such as richness and diversity. So quality filtering is one of the steps in place to minimize that problem. We are also going to filter out sequences that seem unusually short or long for what we'd expect. There are no set rules for making these decisions about what's too short or too long, and it's possible you'd be throwing away something interesting. But once again, just to note that for the most part, broad level community surveys like this one aren't really designed for finding rarities per se, and they are much more likely it's much more likely really short or long sequences are spurious rather than something legitimate. Here I chose 10% longer and shorter than we'd expect our sequences to be as the limits. So let's go ahead and enter the command. So we have vsearch, there's fastqfilter, all of our sequences from the original step. And then vsearch, when denoting these commands, requires a double dash just to note there. And so we are denoting to strip left, and remember it's 19 base pairs in. And then to denote the other side, we go strip right. And that's 20. So then we denote this fastq max e as 1. And then we denote fastq max len as 280. And then we denote the min len, or the min length, to be 220. And finally, we denote our fasta out file, which we will name qseed because we quality controlled them, or merged.fa. All right, we just take a quick look to check everything is correct. And it seems like it is. To get just more information about these arguments, you can go to the vsearch manual that we have below to check, to double check specifically what these are. But let's run this for now. Now it's running. And now we see 186,103 sequences kept. of which 186,103 were truncated, and 2059 sequences were discarded. So this output tells us that these 2059 sequences were discarded due to poor quality and or their length. And note that our output file now is a FASTA file, as after quality filtering, we no longer need to keep track of the quality scores for each sequence anymore. And let's just check if it is indeed looking like our FASTA file. And there it is, our new FASTA file.